It's now time to move to the last presentation of this session, and differently from what we have seen so far, this will not be a live presentation. So since this is a session on reliability, to have a reliable presentation this time, we will go to the video, and while my co-host prepares this, I will introduce the speaker, who is Ms. Phylicia Cicilio, who is currently a research assistant professor at the Alaska Center for Energy and Power at the University of Alaska Fairbanks. She received a BS degree in chemical engineering in 2013 from the University of New Hampshire-Durham in the US, and received the MS and PhD degrees in electrical and computer engineering in 2017 and 2020, respectively, from Oregon State University. During her studies, she worked with peak reliability, which is the ISO in New England, One Power Africa, and Idaho National Laboratory. Her research interests include power system reliability and resilience, dynamic modeling, and rural electrification. I see we are ready with the video.
Hello, and thank you for attending this talk today. This is Phylicia Cicilio, coming to you from Fairbanks, Alaska, and I'll be talking about our paper called Electrical Grid Resilience Framework with Uncertainty. Today I'll go over the motivation for this work, the developed resilience framework method and metrics, a case study that looked at the resilience impacts of transient stability effects from distributed energy resources with accounting for uncertainty. Then I'll go over the concluding thoughts and next steps. The ultimate motivation for this work was to create a cost benefit for resilience analysis, and that way you can have a resilience value stream for entities or utilities that are trying to evaluate improvements that they're looking to put on their system, and is there a resilience value. The cost of having low resilience systems in the United States, this is due to weather-related electrical outages, has been between $20 and $55 billion annually. So there is a strong need to consider resilience when implementing new improvements to utility systems. Now, resilience types of events, as I'm sure most of us are familiar with, we're talking about high impact, low probability frequency events. These are such as hurricanes, storms, floods, and human threats such as cyber attacks. So the goal is to go from a resilience-based improvement to a decision on that, like a go, no go. And in order to do that, you need to have be able to put a value to the resilience and do a cost-benefit analysis. And in order to do that, you need a resilience framework and metric. So this work was did not start from scratch. So we looked to existing resilience frameworks out there, and we decided to base it off of two in particular. One is on the left, called the Resilience Trapezoid by Dr. Patelli, which is a very common resilience framework, and then which is used in power systems. And then on the right, we have Dr. Rieger's resilience-based metrics and framework, which was designed for use in control systems. And one significant difference between the two is the resilience threshold, which is a way to define the minimal normalcy of what is expected or needed in a system to say that you are operating in a way that is acceptable. And so we use these two frameworks to go forward to make ours. So we built out our framework with the following goals: to include the resilience threshold, which is based off of the idea of minimal normalcy, determine the overall resilience value, have a cost-benefit analysis, and this will allow us to compare value and costs of improvements across different events with the aim towards those improvements having resilience value. So below you can see our framework. There is that dotted line, which is the resilience thresholds. The curve here is actually flipped upside down, as that's for the resilience indicator metric that we used in our case study. This is the way that the framework made sense, so that's why it's inverted here. So you go from the predetermined state into the disturbance progress in phase 1 to phase 2, which is post-disturbance. So the event is over, you're in a degraded state, and then you start to restore in phase 3 and enter a post-restorative state. And so you can see the curve of a unresilient system is going to go above that resilience threshold, and a resilient system, which is that dotted line, would stay underneath that resilience threshold, so you're maintaining that minimal normalcy through the event. So that would be the ultimate goal. But if you can't stay underneath that resilience threshold, then you want a way to be able to value how resilient or unresilient is that system. And so here we're using area under the curve. This area under the curve is similar to previous methods, including the resilience trapezoid. And we have, by adding the resilience threshold, we're creating this positive and negative space, where the negative space is adaptive insufficiency, and this is the same term as used in Craig Rieger's resilience framework, in adaptive capacity, and that's the positive. So on the picture here, adaptive capacity are the yellow triangles underneath the resilience threshold, and above the resilience threshold is the adaptive insufficiency area, so that would be negative. So this would be a very unresilient system. And so you very simply add these two areas together to determine your resilience value. So ideally you want that resilience value to be positive, or you could set different amounts that would determine whether or not you determine that system has the resilience that you need. And so then applying this to a cost-benefit analysis, we're looking at evaluating that cost of putting in your improvement versus the cost that this improvement can provide. So that's the cost of system degradation over the event duration. So it's also specific to an event that you're looking at. And then you subtract the cost of that change, which is your improvement, and divide that by the event probability. And the event probability here is in terms of how long is it in between each event that you would expect. They'll go into this deeper in the case study. So in our case study, we looked at the resilience impacts of transient stability effects from DERs, but we also included uncertainty. Our power system test case is the 2000 bus Texas synthetic grid. This is built out by the folks at Texas A&M University, and it is synthetic. It's not real, not the actual ERCOT system, but the synthetic system is built up using public data, so it's supposed to be very realistic and is based off the footprint of Texas. This case study includes all the dynamic machine models for all the generators. This includes wind, and it also has protection simulated with undervoltage and underfrequency relays for generators and loads, and overcurrent protection relays on lines. The event simulated is supposed to simulate a hurricane, which would be a high impact, low probability event that would pass through coastal Texas. The approximate area which this event passing through, you can see with the little black arrow, and it was modeled through 9 successive line outages, which were a three-phase fault followed by both ends of the line opening after 6 cycles. And all these line outages occurred within 10 seconds. For this case study, we looked at several different scenarios for the system. And so we had the baseline system without any distributed energy resources, which showed that 0 DERs, which was labeled A. And then we increased the amount of DERs in the system from 10% to 50%. And this percent that I'm talking about is in reference to the amount of load at each load bus. So it was scaled, the amount of DERs at each load bus was scaled to the amount of load at each individual bus. So it wasn't a flat amount where, say, there was like 1 megawatt of distributed resources every load bus. Instead, if there was, say, 100 megawatts of load at an individual load bus, then if 10% DERs would be then 10 megawatts of distributed resources. And so that was scaled through each load bus through the system. And then scenarios E through G included uncertainty. And so that included those ranges listed there. And these were modeled with, the uncertainty was modeled with Monte Carlo sampling method. Now, the assumptions we did included was the degradation phase was simulated by the transient contingency, which is the 9 consecutive line outages. The post-disturbance and restorative phases were assumed under a steady state recovery, where the mean time to recover for load was at 100 megawatts per hour. The resilience threshold was set to the maximum amount of load loss from any single contingency. This is in line with the North American Electric Reliability Corporation standard for contingency reserves, so the amount of contingency reserves that are required in the system is equal to the amount of load loss from any single contingency. And so it is assumed that theoretically a system should be able to have those reserves available, and that would be that resilience threshold expectation. And now for the resilience value and cost benefits, the operating level that was used to determine those values was the lower 95% confidence interval. And now for the results of the case study, the top row is the dynamic or transient response of those 9 successive line outages, which occur all in the first 10 seconds. And you can see this is showing the total load loss. So the lower the load loss, the better. And on the left column, you can see scenarios A through D. So this is increasing from DER resources from 0% to 50%, that you have an overall reduction in total load loss. This is positive. And then on the right side for scenario G, it shows the uncertainty involved, where uncertainty is between 0 and 50% of that outcome, where you have the standard deviation in the 95% interval, which here is very close to the mean. And this is what was used for valuing the resilience. And then on the bottom is the steady state response, which is using the mean time to recover assumption of 100 megawatts per hour. Now, to determine the cost benefit, the assumptions used here was an event probability of 10 years. So you could assume that perhaps this event would happen once every 10 years. The total event duration, which is taken from the original scenario of 0% DERs, is 55 hours. We did an assumed electricity cost of 9 cents per kilowatt hour with a DER sellback rates, what the utility was paying for those DERs, of 9.6 cents per kilowatt hour. And all these would be customizable to whatever system the utility is working in, and this is what was used for the Texas system based off of publicly available data. And here are the final results, where you can see that there is an increase in the resilience value and cost benefit going from 0% to 50% DERs. However, then when you include uncertainty analysis, the overall benefit drops. However, for among the set of uncertainty scenarios, the scenario with 0 to 50% does have the highest cost benefit. So DERs do provide an increase in resilience using this method of metric, and uncertainty will degrade the actual overall value, so it is important to include uncertainty. For concluding thoughts, we would like to state that including a cost-benefit analysis is very important for any resilience work. This is what's going to enable any entity or utility to be able to actually do something with a resilience improvement and compare in between. And then in our case study, we showed that DERs can provide a resilience benefit. Moving forward, looking to include computationally faster uncertainty quantification methods improved event development methods, including accounting for additional timeframes beyond just the transient and steady states, and inclusion of co-simulation of communication networks to model cybersecurity attacks. So our funders for this was the Department of Energy, and this work was done under the Miracle Project, which is the Microgrid's Infrastructure Resilience and Advanced Controls Launchpad. And this was worked on at Idaho National Laboratory and with assistance from Oregon State University. Thank you very much, and please contact me if you have any questions. Thank you.
Okay, so the author is actually with us, of course, so please, you may send your questions through the classical Q&A function. Perhaps I should start this. Again, Phylicia, if you're with us now. I don't know if you, okay, thank you. I was a little bit, it was a little bit unclear to me why, first of all, you need to normalize the cost and benefit expressions. Why not go with, let's say, the absolute dollar value of cost and benefit?
Normalize it. Oh, I wish I had the. Let me see if I can pull up the slide again.
Yeah, that would be good.
To see your comparison.
Yeah.
Oh, so the purpose of having it in dollars per hour was so that you can compare
maybe
more
you
easily.
wish to share your screen.
Oh, yes. Let's see.
Yeah.
Share
So look
screen.
into the slide.
And share. All right. Sometimes
Okay,
there can be a delay. But
Yep.
there you go. So the purpose of having in dollars per hour was so that you can compare between different events that were of different length. And so some events are going to have a greater severity or duration. And in this way, you could also say, basically add up your cost benefit for multiple events. So say you want to consider a hurricane, but then you also want to consider a cybersecurity event, and you want to include both types of events in the cost benefit. Then this is a way to do that, because it basically to add that dollar per hour together, and you get greater amount.
Yeah, but could you not do the same with the dollar?
I guess we liked the fact that it was per hour because of the variability between the duration of events. And so it gave a better idea of the impact. You could do it per dollar, but we chose to do it per hour because of the variability of the duration of events, and because we wanted to be able to consider all different types of events.
Okay, thank you. I may come back to that later, but now we have two more questions from the audience. First of all, we have again Professor Keith Bell from Strathclyde University. So Keith is not sure that he has interpreted the result times series plots correctly. Maybe you want to go to this plot. It looked like more than 10 gigabytes of demand was lost and then restored within a few seconds. If Keith has interpreted that correctly, what was the mechanism by which this happened?
So 1 second, I'm just going to read that.
Yep.
So yes, this has been pointed out to me before. So the DERs are modeled dynamically, so you can have a reduction in, and then they'll also react to the swings because it's modeled with the DERA Power World model. So they will react to the voltage and frequency swings, and that will cause the upward swing, which will look like a demand was lost, but it was actually the swing of the DRs.
Okay, that's clear. Now we have Dan Molchan of Georgia Tech, who is saying, thank you for your presentation. Are there any limitations in applying your approach to other types of extreme events?
So one part that I really want to expand on is the way we looked at this was at the transient response and the steady state response. And there's a lot of, there's additional complications in between those time frames where you can have different responses that aren't being captured. So I would say limitations would be if there's something in the time scales between that transient response and your steady state and the simulation. You'd want to change the simulations that you do to account for that. And currently we're not looking at interactions with the communication network, and that is an area that we would want to look at in the future so we could account for cybersecurity type events.
Okay, maybe just before we close the session, one more quick question from an anonymous attendee. The question is, how do you merit the improvement in the dynamic response with the resilience metric chosen?
I guess, could I get clarification on merit the improvement in the dynamic response?
Yes, I see your point. So I'm sorry, I don't know who is the anonymous attendee, but please provide the clarification. Or better perhaps, since we are running out of time, please feel free to email Phylicia to have this discussion offline. I would now like to thank all the participants of this session, the presenters of these very interesting papers, as well as the attendees. And it is now time to close. Thank you very much for your participation.